Good afternoon.
Afternoon.
All right, so you should have, I posted exam 2, your grades, your graded work, and the solutions are up on Canvas, so you should be able to take a look at those, and if you have any questions, let me know. We have one more example from chapter 11 to cover, and then we'll move on to chapter 12. So we're going to do problem 11.20. All right, so 11.20 says a concentric tube heat exchanger for cooling lubricating oil consists of a thin-walled inner tube of 25 millimeters diameter carrying water and an outer tube of 45 millimeter diameter carrying the oil. The exchanger operates in counterflow with an overall heat transfer coefficient of 55 watts per meter squared Kelvin and the tabulated average properties. So they give us a table of properties, so density, specific heat, kinematic viscosity, thermal conductivity, and Prandtl number for water and the oil. Okay, and then they also give a schematic, and some of the temperatures and mass flow rates are on there for the water and oil. And then it asks for part A, if the outlet temperature of the oil is 50 degrees Celsius, determine the total rate of heat transfer in the outlet temperature of the water. Part B is determine the length required for the heat exchanger. All right, so we have then a concentric tube heat exchanger. It's got a thin, actually let's write this out. Let's do it like that. Heat exchanger. All right. Thin-walled inner tube. Okay, and it's counterflow. It has an inner diameter of 25 millimeters, an outer diameter of 45 millimeters. The overall heat transfer coefficient is 55 watts per meter squared Kelvin. All right, so then we have some stuff on the oil side. So the oil, they give us a mass rate of the oil is 0.1 kilograms per second. They give us the oil inlet temperature of 100 degrees Celsius. Oil outlet is 50 degrees Celsius. And then we have the water side, and they give a mass flow rate on the schematic of 0.1 kilograms per second. And the water's inlet temperature of 30 degrees Celsius. All right, so then they want us to find part A. It's the total rate of heat transfer. Q. The water outlet temperature And then part B asks for the length of the heat exchanger. Let's write that a little nice, neater. Okay. So that would be L. Properties down here in a minute. All right, let's do our schematic. Okay. So we have oil on the outside tube, water on the inside. Counterflow, so the directions are different between the oil and the water. Okay. The inner diameter was given and the outer. All right, assumptions. Let's do steady state. Okay. So properties. So they gave us a whole bunch of properties, and I'll do that in a table here. So we have water, oil. They give density. They give specific heat, kinematic viscosity, thermal conductivity, and Prandtl number. All right. Fill that in. Okay. All right. So now we can finally do our analysis on the problem. Okay, so we have this concentric tube, so one tube inside of another. The inner tube is thin wall, and it's counterflow. So you have flow in one direction of oil, water in the other direction, right? Give us the diameters, give us the overall convection coefficient. We have mass flow rate, the inlet and outlet of the oil. We have mass rate in the inlet of the water, okay? And a whole bunch of properties. And for part A, we're looking for the total. We're looking for two things, right? total rate of heat transfer and the water outlet temperature. Starting with the total rate of heat transfer, where do we start to solve that?
The COE.
Oh, good.
COE on what? So we can do a COE on the water, we can do a COE on the oil, we can do a COE on the oil and the water. And we got to choose our boundaries.
I mean, I get it. It's kind of.
I would say
That's
the
like a
oil,
significant
because we
jump,
have
so.
both of those temperatures.
Yep. So we have the inlet and outlet of the oil, and we have the mass flow rate. All right. So it would be the COE on the oil. It'd end up being, open system. And if we neglect kinetic energy, potential energy, no work, steady state, and we just have mass flow rate carrying in enthalpy, mass flow rate carrying out enthalpy, and that's heat, we can simplify it, and we'll end up just getting something that looks like this if we simplify the open system COE, right? So if we look at this now, we have the two temperatures of the oil, as was mentioned. We have the mass flow rate of the oil. In our properties right above, we have oil, okay? So nice and straightforward. We can get Q. So we get 9,500 watts, or 9.5 kilowatts. So that's the total rate of heat transfer that's occurring. Basically, we chose the COE of the oil, right? And we solve for Q, okay? What is our, for the second part of part A, it's asking for the water outlet temperature. What do we do for that case?
Same Q, right? So we could just substitute everything back.
Yeah, so the heat is the same amount. What's leaving the oil is going into the water, right? So we could just look at the COE of the water. If we really wanted to be crazy, we could do a COE around the oil and water, and then it's just the mass flow rates times CP delta T of each of the fluids, but we already have Q, so there's no reason to go around and be crazy like that, right? So we'll do the COE of just the water side. Again, it's open system. And if we do that, mass flow to water, again, same simplifications. Kinetic energy, potential energy, it's steady state, no work. So you just have mass flow rate carrying in and out enthalpy and heat transfer. Okay. So when we looked at this above, I should also say this was out on our heat transfer, and then this ends up being in. All right, so let's look. We have the water inlet. We don't have the temperature out, right? We have the mass flow rate of the water was given in the problem. CP is in that properties table, and we already solved for Q. Okay, so we have our one unknown is the water outlet temperature, and that's 52.6 degrees Celsius. Any questions on that?
Yeah. So if we were to do this type of problem for an exam, you would want us to write those extra assumptions to get this cancellation, or?
No, I don't necessarily require it. You get more partial credit, like it's in my other tests. If there's leaps that are done, then the leaps better be right, right? So then if there's a leap done and it's wrong, there's nothing I have in between to give you, right? So if you on exam do this and it's right, then that's fine, right? But if, now it looks like some made up COE that isn't quite what you see here, and it's some other terms but not correct with something that's within the COE, then that's where you get that whole section wrong. Okay, but assumptions wise, sure. Again, that's just knowing your assumptions correctly. So that's where you have neglect, kinetic energy, and potential energy is the only other one. The other stuff, there's no work. It's not even in the diagram. So it's really just the kinetic and potential energy that would be neglected, and incompressible fluid.
Yeah.
Right. That goes with that COE that was used in this equation that was brought to us back in chapter 8, which is this one, which you see. All right, any other questions? All right, so far, it's really just a thermal problem, right? That was just thermodynamics, something I could ask you in Thermo 1 with the COE. Okay. And now part B asks you for the length of the heat exchanger. So now we're getting into the size of the heat exchanger, which is not a thermal problem, right? We didn't do anything with sizing components like that. All right, so now we need to figure out the size of the heat exchanger. So where can we begin with that?
Also
Thermal
page
circuit.
kind of thing, not like
Thermal circuit. So in the other problem, yes, right? But there's one key thing that was given to us in this one. And if it wasn't, then yes, we would need to. So we were given the overall heat transfer coefficient, right? So if we go back to our last problem we did last class, right, we were given diameters, thermal conductivity, and we had to set up our thermal circuit and use that thermal circuit to get the overall convection coefficient and or area, right?
Since we have it, then can we just use the 1 over UA is equal to either the inner or the outer?
Yes. Yeah, because
that way.
Yep. Yeah. So they gave it to us in this problem, so it kind of skips those steps, but it makes the problem a shorter problem. So I chose this on purpose so we didn't have to. I had the first example more deal with figuring out that overall heat transfer coefficient, and the second example that we're doing now more into the other parts of it. Okay, but you could have a problem that requires you to do both, and it can get lengthy, right? Because now you're doing the thermal circuit and going through all those steps to getting all those different resistances, right? So one thing, yeah, you mentioned another thing about the inner or outer, okay? Well, in this problem, there actually isn't an inner or outer heat transfer coefficient because it gave us this thin-walled inner tube. So we're basically neglecting the wall resistance or wall thickness. Okay, so the inner and outer diameter isn't this diameter that was given here. Okay, because it's saying there's a wall here, but we're neglecting that thickness. We're just saying it's just this. Okay. All right, so we have that overall convection coefficient, so we don't have to go through those steps of the thermal circuit. Okay. All right, so then knowing that, so if we weren't given that, we would have to go through those steps. So then what would be the next thing to do? All right, we're figuring out length. And there's actually two ways we can go about this. Okay. So we went over in chapter 11 two methods, right? So we can start with, we'll do the log mean temperature difference as our first choice. Okay. Or just the first one we're going to do. If we look up that, it looks a lot like, we introduced it a little bit in chapter 8, and it comes back in again in chapter 11. And it's just overall convection coefficient area in this log mean temperature difference. Okay. And in this problem, we're counterflow. So the CF means counterflow. And it has this log mean and not just delta T, because the temperature is changing as it's going through the heat exchanger, right? From the inlets to the outlets. So the log mean takes into account that change. Okay. All right, so let's look here. We already solved for Q from our COE. We mentioned we have the overall heat transfer coefficient. So we need area and our log mean temperature difference. What's the area?
Walking around, and
IDL.
I see kind of that name.
I didn't catch it all, but
IDL.
I like, and I mean, yeah.
yeah, pi dl. Okay, so, and it's going to be that inner diameter again, because in this case, the inner diameter is talking just about the diameter of the water tube, and it said the outer diameter is the oils tube. Okay. All right, so we are ultimately trying to find length. So this is our ultimate goal, is that length term we just have in this area. All right, we have diameter. Okay. All right, so that means we need the log mean temperature difference. And that equation looks like this. Okay. Now for counterflow, we have delta T1 and delta T2 are different depending on when it's parallel flow or counterflow. Let's see if I can find it quick. There we go. All right, so delta T1 is the temperature of the hot inlet minus the temperature of the cold outlet. Delta T2 is the temperature of the hot outlet minus the temperature of the cold inlet. Okay. And for us, which one's the hot one? Which one's the cold fluid?
The oil's hot and the water's
Yeah, so we're transferring heat from the oil to the water. So the oil's considered the hot fluid, water's considered the cold fluid in this problem, right? So So that would make oil inlet, water outlet, oil outlet, water inlet, okay? And we have all the temperatures because they were given or we solved for it. So that means we can solve for delta T1, delta T2, and the log mean temperature difference. And we get 31.8 degrees Celsius. So this and this is all for counterflow. Okay, the delta T1, delta T2 are this equation is the same. So this is parallel or counterflow. But what is delta T1 and what is delta T2 changes depending upon whether you're counterflow or parallel flow. Okay. And this is equation 11.17. All right. All right, so we go back up. We have this. So then the only unknown now is L. So we get 69.3 meters. Boom. Okay. Questions on that? All right, so that's just one method of getting this. We have the other is the effectiveness NTU method. Okay. So we're going to, again, solve for L, but using the effectiveness NTU method, right? So effectiveness, if we remember from our slides, lecture, is Q over Q max in NTU, number of transfer units, is U over UA, our overall convection coefficient, or overall heat transfer coefficient times area over the minimum heat capacity rate. Okay. All right, so we have what effectiveness is, what NTU is. If we go through, we know Q, right? So we know Q max. They gave us overall heat transfer rate. So we don't know our minimum heat capacity rate. And then area, we already labeled it above, but pi d L. All right. Okay, so that's kind of the main beginning of those two equations. So where do we think we're going to go first? Are we going to be solving effectiveness and from effectiveness getting NTU? Or are we going to be getting NTU and then using that to solve for effectiveness?
Effectiveness and then NTU.
Yeah, so we need to figure out effectiveness. So Q max is our minimum heat capacity rate, the hot temperature inlet minus the cold temperature inlet. Okay, which is just, in our case, the oil in, water in. Okay, so we have temperatures. And then we don't have the minimum heat capacity rate. So this tells us the maximum that heat that can transfer from the one fluid to the other. Right, the minimum heat capacity rate and then the largest temperature difference is the inlet. So that's the max that could ever be transferred. All right, so looks like we need the minimum heat capacity rate. How do we get that?
It's for whichever heat capacity rate is the lowest, I think.
Yep. So let's look at cold fluid, which is just our water, which is mass flow rate of the water times the CP of the water. Hot is just the oil in this case, which is the mass flow rate of the oil, CP of the oil. Okay, the water ends up being 420 watts per Kelvin, and oil ends up being 190 watts per Kelvin. So this is how good the fluid is as absorbing heat, right? So we compare them, like was said, and that means this is our max 420 and the min is 190. Okay, so it could be dependent upon the heat exchanger you're looking at. It could be the cold fluid, it could be the hot fluid that ends up being it. So you got to solve them and then compare. All right, so looking back at our equations, we have our minimum heat capacity rate. So that means we can get Q max and then effectiveness. All right, so we get our max heat capacity rate, 13,300 watts. So that's the most that could be transferred with a infinitely large heat exchanger. So we get effectiveness, which ends up being, where are you? Okay, 0.714 or 71.4%. Of that max. Because from our CUE, we got Q, the actual heat that we're going to transfer. All right, so now we have effectiveness. So we need to get, then we have effectiveness, now we need to get NTU. How do we do that?
Using the overall heat transfer and then that Cmin in your area.
So, well, we don't have, so in this way, we don't know length, right? So I'm saying we're going to solve for length as an unknown, okay? So we're not going to know area. We're going to solve basically for area. So that means we need to get NTU, right? We need to get this value because we don't know area, okay?
Could we use one of the tables?
Yeah, so there's a table. We have table 11.3. That goes from, it shows effectiveness as a function of NTU. So that basically goes from NTU to effectiveness. And then table 11.4 goes from effectiveness to NTU. Okay, shows equations for that. Okay, so you basically look in the table and you see what flow arrangement you have, right? We have a counterflow heat exchanger. So we look in that equation 11.29b. Okay. And we can use that equation, or you can use the figures. Okay, and again, we have counterflow, and that ends up being figure 1111. Okay, so I'm going to use the figure, okay, to get a quicker answer. And if we look at this figure, it basically gives us NTU as our x-axis, effectiveness as our y-axis, and then we get a few lines here. Okay, and they are labeled as the minimum heat capacity rate over the max. Okay. And so that one's 1. They have, say, this one's 0.25, and they're all labeled different ones. So we know effectiveness, right? So we'll basically have to go find our effectiveness. We need to get our minimum heat capacity ratio over max, and then we can use that to get our NTU. Okay. All right, so we need heat capacity ratio, which is minimum divided by max. If we do that, we get 0.452. When you use these figures, though, it's going to be more of an approximation because you're not going to get many decimal places looking at these figures when you pick a point. So I got about 1.5 for my NTU. And now we go back up. So we now have the NTU, and we can then, only thing unknown is area, and then area equation, only thing that unknown is length. So I got 5.182 meters squared, and then the length I got 66.0 meters. Okay. If we use the equation, so we got 66 in part with the effectiveness NTU, we got 69.3 with the log mean temperature difference. If we use the equation form of, here, 11.29b, we would have got the same answer as using the log mean temperature difference. It's just, this is all just error in reading the figure. Any questions? So in this problem, we went from Q to effectiveness to our NTU from those tables of equations or figures to our U times A, right? But you can also go from UA to NTU to effectiveness to heat, right? And or you can go from temperatures when you got heat. So it just depends on what your kind of problem you're solving. This first example, first one case is more of a, design, sizing kind of problem because you're sizing the heat exchanger. We got a length, right? The second way, you have a heat exchanger already picked out because it has geometry, it has overall effectiveness, so you can get that value. It has those things. So then we're trying to see, in this case, when we work our way, it's more of a performance. Because we have this heat exchanger, how well is it going to perform in this application? Or at these temperatures, right? The other thing to think about is when you go this route down here, this one, it does not require you to know any temperatures at the outlet. So required to be given. So you only just need inlet temperatures to go that route. If you had no outlet temperatures with the log mean temperature difference, it becomes a little trickier. And an iteration is the only way to solve these sets of equations if you have that case, the performance case, because you need temperatures to get Q, right? So that's where you'd have to iterate these sets of equations to get there, to get your answer. The COE and the log mean temperature difference, those set of equations you would have to iterate through to do a performance problem, where there might be an additional step in the log mean, in the effectiveness NTU for the design sizing, but it works for either performance or design sizing problems. Okay. Any questions?